Hello everyone, I am Mike. As you have known, I am a Udemy instructor specialized in the utility and energy industry. So in this video, I'm going to provide you with a mini lecture on cable rejuvenation. Now for this mini lecture, I will be your guide where I will teach you about cable rejuvenation as well as referencing other videos on YouTube as we progress. My aim is to get you the knowledge you need by using my material as well as other YouTubers' material to maximize your learning experience. As such, you will see that at multiple points of this video, I will direct you to watch another YouTube video. When that time comes, please refer to the YouTube links in this video's description and click on that video link. I recommend you to use a computer for this video, as when prompted you to view another video, you can then conveniently pause this video, right-click the link that I recommend you to watch, and view it in another tab. Then you could close that tab once you're finished and then resuming this video. So now, let me be your guide in this cable rejuvenation learning journey, and let's get started. Let us start off with the question, what is cable rejuvenation? Well, basically, we are restoring power cables. Silicone fluid is injected into the power cable and fills the strand region during cable rejuvenation. The fluid comprises a combination of components that heal water tree damage, inhibit new water tree growth, and in some situations update the cable with current cable ingredients. The fluid seeps through the insulation and conductor shield. This diffusion mechanism permits the injected elements to flow from the strand to the insulation where the water trees are located. The amount of injection pressure utilized has a significant impact on the rate of rejuvenation. By filling the water trees, delaying the development of new water trees, and in certain situations, improving the insulation qualities to those of new cables, the injection fluids affect the chemistry of the insulation and the physics of the cable to extend the circuit's dependable life. There are 7 reasons to adopt cable rejuvenation. The primary motivation for circuit owners to employ cable rejuvenation nowadays is to save money. In most cases, the cost of rejuvenation is half to 1/3 of the cost of cable replacement. If the region is heavily manicured, difficult to reach, or the soil is actually rocky, the cost reductions can be much larger. The circuit owner may stretch their capital budget 2 or more times with cable rejuvenation and have a greater influence on their grid's dependability. Now, the process of cable rejuvenation is also quicker than that of cable replacement. When opposed to replacement, rejuvenating a cable typically takes 1/3 of the time. And when the circumstances calls for it, this enhanced production permits the circuit owner to spend year-end money more quickly. Now, the third reason is that there are reduced impact on the environment. The cable rejuvenation eliminates new pollution, no resources are used to manufacture new cable, no diesel fuel is used during installation, and the environment benefits when cables aren't left in the ground. Next is that cable rejuvenation leads to fewer outages. There are fewer instances when consumers will be without electricity, since utilities can rejuvenate ahead of time rather than waiting for an emergency, which is when the cables fail. Customers enjoy relative service continuity even during injection, as opposed to experiencing scheduled interruptions as necessary for cable replacement programs. The fifth reason is of its low failure rate. Hundreds of millions of feet of cable have been rejuvenated in the last decades, and cable rejuvenation has been employed by more than a few hundred utilities spanning across continents, and their accumulated post-injection failure rate is actually quite low, as less than 3.5% throughout that entire decade of time. And of course, this is a very low and good percentage to have, and it shows that cable rejuvenation has a very, very low failure rate. Now, the sixth reason is that it has low customer impact. Cable rejuvenation is preferable to cable replacement by hand digging, trenching, or boring because it impacts the customer less, as it is less intrusive. There's no noise from the equipment, the injection equipment, because the injection equipment is compact, the procedure is quick, and established landscaping is almost unaffected when you are doing cable rejuvenation. And 3 to 5 cable segments can usually be finished every day, practically silently and without causing any nuances to the customers that are close by. Finally, the seventh reason is that it can be capitalized. Cable rejuvenation has been allowed for capitalization by a lot of regulatory bodies such as the FARC because it increases the functional life of the cables beyond their initial projected lifespan. So now let us take a look quickly in a short video of generally how cable injection works. Please pause this video and view the recommended video in a new tab and resume this video when finished. The link is in the video description titled How Cable Injection Works. So coming back from watching that video, let us start off with looking at electrical cable degradation. Now, what problem cable rejuvenation solves is actually cable degradation. Now, the two types of degradations that we need to worry for cables are wet and oxidation degradation. Let us start off with wet degradation. Power transmission, as well as instrumentation and control cables, require durable and dependable polymeric dielectrics. Because of environmental conditions that might damage cable insulation, cables used in underground residential distribution, or what we call URD, confront substantial issues over time. Moisture and electrical stress can cause the dielectric characteristics of the polymeric insulation to gradually deteriorate and eventually would lead to full deterioration and finally failure. Initially, only voids and minor defects will form on the cable. However, the formed cavities will propagate through the polymer insulation and expand into tree branch forms over time. Humidity, when combined with an AC electric field in a type of environment seen in underground cable installations, can cause water trees to expand. And when the electrical stress on developing water trees becomes too much for them to handle, an electric tree forms. Water trees' time-dependent growth and extension can drastically diminish the usable life of power cables. Now, water and electrical treeing aren't the main causes of polymeric insulation degradation in electrical cables. Failure can also be caused by a complicated mix of processes. Radiation and heat stress can produce what we call dielectric oxidation, and the mechanical stress can cause fracture propagation across the dielectric owing to oxidation-induced embrittlement. The production of radical species initiates and maintains oxidation in polymers. And due to thermal vibration or high-energy photons, chain scissions produces free radicals, which subsequently combine with oxygen to form high-energy activated moieties. The auto-oxidation process is then repeated when these radicals react with another molecule to reduce their energy state. The use of antioxidants in dielectrics, such as bulky phenols or hindered amines, is known to reduce auto-oxidation by consuming these free radicals as they are being created. Antioxidants and other additives replenished by cable rejuvenation may prevent free radical generation and minimizes cable failure risk by slowing polymer breakdown. Now, there are some cases where cable rejuvenation just doesn't work. For example, cable replacement is the sole option when circuit owners need to raise the ampacity of the cable run or the voltage of the line. Furthermore, because the fluid must be allowed to flow between the cable strands, solid core URD cables cannot be rejuvenated. There is an exception to this, however, as some solid URD cables have stranded feeder cables in there that are suitable candidates for cable rejuvenation. Some circuit owners began employing strand block cables in the mid-1990s to prevent water from migrating longitudinally in the strands, and unfortunately, this also hinders the process of rejuvenation. Now, before we move on further into our course, let us take a brief look at our sponsor for this little mini course on cable rejuvenation. Now, as an engineer, especially when I first started in my career, I really felt overwhelmed the list of documents that we need to do on top of our technical work. Yet, these documents are very important in our career as it is the more prominent thing that displays our credibility to management and to our clients if we so decide to become an engineer consultant, which is where the actual money is. Now, I don't have these tools available for me when I first started my career. But now, PM Milestone has created this package of all the professional templates that you need so that you can focus more on the technical aspect of your career. These templates are tried and tested by real professionals, so you should feel confident in using them in your career to present your best foot forward in front of your manager or your clients. These templates are also updated periodically, so I think their last updated date is actually in 2021. So they're not going to be out of date or out of context to the present times, as these people are actually very serious in getting the most professional product to meet your needs. They're also very confident of the quality of these templates too, as they offer you their product completely risk-free with 60-day money-back guarantee if you are not satisfied with it. So if you're interested in this product and would also like to support me in creating these mini courses on YouTube in the future, please check out their product using the link in my video description below titled Course Sponsor PM Milestone 2.0. So coming back from looking at my sponsor, let us look at the cable rejuvenation processes. Now, over the years, engineers have created a range of injection fluids and methodologies, allowing operators to deploy customized operations based on the cable type, occasion, or environment. Now, the method may also be easily adapted to other cable arrangements, including splices and other connector types. In some circumstances, technicians would dig 6-foot square splice excavation trenches that are 4 feet deep in order to deal with those. And the impact of these pits on landscape is significantly less than that of trenching or digging, which is generally necessary for cable repair. Unsustained pressure rejuvenation and sustained pressure rejuvenation are the two methods for cable rejuvenation. So let us start off with unsustained pressure rejuvenation first. Unsustained pressure rejuvenation, or short named as UPR, injects low pressure fluid into the strands through injection elbows or live front terminators. And they are, the low pressure is around 10 to 15 psi. Now, it is occasionally feasible to flow liquid or fluid through splices due to the low pressure injection. Only around half of traditional molded splices allow for this type of flow, whereas tape splices, pin and socket splices, and shrink to fit splices would not be able to. Now, the unsustained pressure rejuvenation procedure is often used in places that are difficult to reach or replace due to expenses and cost. Low pressure is used in this operation, allowing fluid to flow through splices while the circuit is actually energized. And the procedure is what you see in front of you right now. So the first step is to isolate the damaged cables. You test it and then ground it. And then next, you would check each section for splices, neutral corrosion, and overall length using a TDR equipment. And TDR stands for the time domain reflectometer. Then moving on from there, you got step 3, which is to confirm that the rejuvenation fluid will flow adequately by performing what we call an airflow test. Then moving on, we got step 4, which is replacing the connectors and injection elbows as needed. And then in step 5, at one end of the cable, we should connect a feed tank to the injection elbow, and we should connect a vacuum tank to the other injection elbow. And lastly, in step 6, we will need to re-energize the cable section and start the injection procedure with the transformer closed. Sustained pressure rejuvenation, or SPR, on the other hand, injects fluid into the strands at a modest pressure using injection adapters, and the pressure is usually around 1 to 300 psi. Now, to facilitate prolonged pressure injection, legacy splices, which are typically of dubious dependability, are usually going to be replaced. In as little as 7 days, the sustained pressure rejuvenation method rejuvenates the insulation, bringing the dielectric strength to that of a new cable. And early cable failures can be avoided because of this quick rise in dielectric strength. And it also permits additional fluid to be injected into the cable, prolonging its life by up to 30 to 40 years, which is actually quite a bit. So now let us look at the procedure. So in here, as you can see in front of you, we've got a 4-step procedure. And of course, the first one is to isolate the damaged cable, test it, and then ground it. And then the second step is to check each section for splices, neutral corrosion, and overall length with, of course, again, the TDR equipment. If splices are found, the field guys should use a radio frequency locator and a measuring wheel to locate their positions. And then afterwards, the locations located, they need to dig a trench to expose the splice and replace them with new splice connections and injection adapters using templates to assure appropriate injection adapter installation. Now, the third step is you need to use a reasonable amount of pressure to inject each section. So note that by injecting like 100-meter segment usually would take around 30 minutes or less. So it's actually quite fast. So in this case, the field guys will remove all equipment and install standard elbows at either end of the cable after injection. And then lastly, of course, you re-energize the rejuvenated cable section before you move on to the next section. So now let us look at how sustained pressure rejuvenation works. Please pause this video and view the recommended video in a new tab and resume this video when finished. The link is in the video description titled SPR. Now, as seen in the procedures, the process, cable rejuvenation has largely concentrated on injecting silicone-based fluids into strands of aged medium voltage power cables. Now, the injected fluids move through the cable to water-treating places, react with water, and improve the insulation's dielectric qualities. Right now, I want to briefly discuss the 3 fluid components, namely the phenylmethyl dimethoxysilane, which is the codename PMDMS, the titanium isopropoxide, which is acronymed as TIPT, and the trimethyl methoxysilane, which is just simply called TMMS. By the way, these components are more known by its acronym than its actual chemical names, as you can see that it's very, very hard to pronounce. Due to its strong reactivity with water, the PMDMS was already used in the first generation silicone-based injectable rejuvenation cable fluid. Now, the TIPT was utilized as a catalyst during the condensation stage in addition to the PMDMS to enable cross-linking of the injectable fluid at low weight fractions. TIPT also interacts with water to make what we call titanium dioxide or TiO2 nanoparticles, which have high dielectric characteristics and function as a nanofilter, filling gaps caused by water trees with these titanium dioxide nanoparticles. Now, a second hydroxyl reaction occurs with TIPT, resulting in an oligomer with two monomer units. And because of the density difference, it is believed that methanol will diffuse out of the insulator. And the reaction proceeds until the injected fluid's reactive methoxy groups are completely consumed, resulting in longer oligomers. When the freshly produced oligomers reach a length of at least 5 to 8 units, their viscosity gradually rises until they become immobile, forming a protective coating over the damaged insulator. For these silane-based fluids, silane activity, chain length, rate of rejuvenation, and penetrability are all very important properties. While the aforementioned first-generation rejuvenation fluid was successful in prolonging the life of electrical cables, the difficulties of injecting the fluid into cables and the delayed reaction rate caused the fluid to be distributed in an inhomogeneous manner. A newer rejuvenation fluid mixture consisting of PMDMS, TIPT, and our third component, the TMMS, was designed to speed up the rejuvenation process response pace. TMMS is a silane-like PMDMS, except it penetrates a polymeric dielectric 25 times quicker. Now, of course, with this advantage comes disadvantage. So it was discovered that this composition, the TMMS, contributes also to the corrosion of aluminum conductor strands. Corrosion was addressed while the injection fluid's better penetration capability was maintained by reducing the content of TMMS to around 5%. And finally, let us talk about cost. If comprehensive cable rehabilitation is your objective for a particular subdivision, rejuvenating the most cable segments will save you the most money, even if it means digging a number of cable splice pits, because excavating cable splice pits is typically less expensive and less disruptive than replacing a whole cable segment. At first glance, it may appear to be more cost-effective to merely rejuvenate the easier cable segments. However, when you factor in the cost of replacing the remaining cables, the subdivision's overall capital cost skyrockets. Now, a lot of utility companies, while doing cable rejuvenation, may also consider splice replacements, which are those connectors of cable endpoints. Some utilities may opt to flow through all splices that enable fluid flow if they have never had a splice failure and believe their splices are in good condition. Other utilities have had many splice failures will start to request that all splices be replaced. Lastly, some utilities may wish to replace most splices but are ready to try flow through splices that are difficult to dig due to their geographical location or accessibility, but are economically expensive to dig. Overall, the utility selection should be based on the rate of splice failures. Of course, replacing the splice is the ideal option, but it will be difficult to explain to the regulator, especially if your splice failure rates are low. And this brings us to the end of this course. I hope you enjoyed this mini lecture and have learned a lot about cable rejuvenation. As I've mentioned before, I wanted to try out this new format for materials that I want to teach you, which I wanted to offer to you for free. Now, if you like more of this, please let me know in the comment section, and remember to click share and like and subscribe to our channel. Also, if you want to learn more about power cables, I recommend you to take my Udemy course titled Power Cable Fundamentals, which I left the link in the video description below. Again, thank you, and I hope to see you in my other courses in the future.